11, 3 comma, or sorry, yeah, 3 comma 11. Or screencast rather. What we're going to do today is review transformations of functions in real life scenarios. We're going to focus on reciprocal functions, square root functions, and exponential functions. So let's start with, in each case, I'm going to do question number 2, or the second representation in each of the 3 sections. So all I'll do is the part where you actually determine the equation, and then you'll see how that's done, and you'll be able to do the rest on your own independently. So what we're doing first is let's take a look at the Canoe Graphs, and if you think back to Canoe Graphs, they were reciprocal functions, and x, the variable, represented the current in the water. So that could increase your speed or decrease your paddling speed. And that created that vertical asymptote, because if you paddle at the same speed as the current is at, and you're going in the opposite directions, you'll sit still in the water, and it will take forever. So let's take a look at this data. You'll notice that I've done just a rough scatter plot of this, and just to go over some things here, you can see this point here says error. So at 0, when the current is 0, it creates an error, which is a domain error. Well, that's going to be your vertical asymptote, right? Because that means if you, in this case, x represents your paddling speed, or sorry, x represents your paddling speed, so if you're paddling at 0, you don't go anywhere. Well, what does that mean? I guess it probably means there's no current, right? So if you paddle 0, you don't go anywhere, and it takes forever. You never reach your destination. So your time is infinite. So the y-axis represents time in this case. And the x-axis is your paddling speed. Okay, and that's sort of counterintuitive, but nonetheless, you've gone through that, so you know. So that represents the vertical asymptote. Well, let's take a look at what happens after 20 hours of paddling, or sorry, a speed of 20 rather. So a paddling speed of 20, 30, 40, 50, it looks like you're getting closer and closer to 4 hours. So in this case, that means that you can never quite reach 4 hours. So no matter, even if you paddle at the speed of light, it's going to take you 4 hours. So it looks to me like it took 4 hours to get to the river. Right? So your trip, you had to spend 4 hours in the car to get to the river. And then if you can paddle as fast as you can possibly go, it still takes a little more than 4 hours. So we've got a vertical asymptote, or sorry, a horizontal asymptote. I'm really off my game today. A horizontal asymptote at 4, and we have a vertical asymptote at 0. So in terms of our transformations, the vertical asymptote is our C value, and the horizontal asymptote is our D value, shifted up by 4. So I can now represent that function as f of x equals a over x minus 0 plus 4. And I don't really have to leave the 0 in. So now I've got a general equation that shows the vertical and horizontal translations or shifts. And remember, they are involved with adding and subtracting. So I've got a vertical shift and a horizontal shift of C and D. So now I have to determine the vertical stretch or vertical dilatation A. And there's a few ways I could do that. I could look at patterns in growth in the table. As you grow by 1 each time, what does y change by? There's another interesting way to look at this too, with respect to constant multiples and things. But what we're going to do, we're going to use the same strategy each time to figure out A. We're going to substitute in a point, x comma y, and then we're going to solve for A. So I'm just going to go to the next page to do that. First I'm going to pick a point. Let's pick 3 and 11, so 3 comma 11. It's a nice number rather than something with a decimal like 4.2. So let's go to the next page. So it's just re-recording that right there. Three comma 11, and we know our function is f at x equals a over x minus 0 plus 4. and I'll leave out that 0 from now on. So I substitute those values in the appropriate location. F at x is represented by 11, and x in this case is 3. So in other words, when I paddle at 3 kilometers an hour, the total trip takes 11 hours, plus 4. Now I need to solve for a, and the way I do that is to minus 4 on both sides. 7 equals a divided by 3, and then the inverse operation to a divided by 3 is to multiply both sides by 3, and I have a equaling 21. So therefore, my function f at x is 21 over x plus 4, which means the total distance we traveled in the canoe is 21 kilometers. I'm traveling at a speed of x, paddling at a speed of x, and I have a horizontal asymptote of 4. It's shifted up by 4, which means I am taking 4 hours to get to the river. And that's your reciprocal function / canoe graph example. Okay, folks, here's another example, except this time you can see just by the scatter plot that it's a square root function, and you have to remember that there are domain and range restrictions in the square root function. I think it has something to do with negatives in the square root as what we call the argument, the linear function that's underneath the root sign. We can't have that as a negative. And in terms of the key feature we talked about was cusp, which is the equivalent to a reflected vertex. So that is the cusp. In this case, it's located at 0 and 4. And by the way, this is what's called a supply curve in business or economics. And so the y-axis shows how many items a store is willing to sell at certain prices. So it does follow then, as the price goes up, a store is willing to sell more of an object. So they'll order more in if they can get a certain price. Okay, so in this case, I don't know that we have a horizontal shift left and right because the cusp appears at 0, 4, which is right here. So our cusp is 0, 4, and in this case, if we look at shifting, it looks as though, so normally you would see it with the cusp at 0, 0, so the cusp has been shifted up by 4, just like a vertex, and so that's at 0, 4. So nothing left and right in terms of translations, but it's up by 4. So let's write that. F at x is a over x minus c plus d, and in this case we have a over x minus 0 plus 4. So, and I guess what that would mean, right, is, and this is, I guess, a pretty silly store if they're going to do it, is if the price is $0, they're willing to give away 4 of them. If you can see, if the price is $1, they are willing to sell 10, and so on. So maybe they give away 4 out of some sort of promotion or something, right? And you can see at the very end, if their price is $6, they're willing to sell almost 19 of them. Well, they'd actually have to round up to 19. Okay, so there's a few ways that we can do this in terms of figuring out the a value. We can substitute and solve again, which works certainly. The square root function is really nice, though. You can see the transformation quite well because remember, it's the inverse of the square function, which is normally 135. So we can so the rise is normally 135 on a regular square root. So we know the run on, the rise on a quadratic, a parabola, is 135. So we know the run on a square root function is 135. So we go over by 1, see what we go up by. Then over by 3, and see what we go up by. So you can see in this case, when we went over by 1, we went up by, from 4 to 10, we went up by 6. And then when we went over by 3, we went up by, perfect, 6 again. So we know our A value is 6 in this case. Or you could substitute in, and I'll show you how that starts. If you're going to substitute in, you pick a point. For example, 4 and 16 is nice and easy to pick. So we could have our Y value set at 16. And we substitute in 4 for X plus 4. And if we were to figure out what that is, we would end up with an A value. Let's actually go ahead and do this over here. So I'm going to minus 4 on both sides, and I would get 12 equals Mr. Long, it's just 1 second. And this, folks, is why I shouldn't do this in a rush, and I should do it in advance, because then I wouldn't have done that with a reciprocal function instead of a square root function. Okay, so let's do that again. F of x equals a root x minus c plus d. Remember that when we're doing transformations with square root, reciprocal, and quadratics, we can always remove the horizontal dilatation factor, right, through algebra. So we don't need to actually use a coefficient in front of x when we're working with those types of functions. Okay, so we've got this, and then I put in the transformations. A root x minus 0, because it's not shifted left or right at all, plus 4. It's shifted, the cusp is shifted up by 4. So now I substitute my values in, and the values would be, I'm going to pick that order pair of 4, 16. So 16 equals a square root of 4 minus 0 plus 4. And if we look at this, it's going to be 12 equals 2a, and a is worth 6, which is exactly what we came up with if we did the graphical analysis in terms of the patterns. Okay, so in this case, f of x equals 6 root x plus 4. Okay, and that's our function. All right, one more. And in this case, we're going to do an exponential curve. And you can see here we're going to look at bacterial growth. And remember that when we looked at bacterial growth, there are some bacteria that are capable of reproducing and some that aren't capable of reproducing. So I've already set up the scatter plot there. It's pretty easy to see that in fact it is a exponential growth problem. If you look at it, you can see that 10 hours before the experiment, or before the timer started, that there were 7 bacteria. And what that indicates is that we have a horizontal asymptote, obviously at 7, right? So that means that there are 7 bacteria that can't reproduce, right? That's a constant. They're not growing. And then at the start, so we have a horizontal asymptote at y equals 7. And the other thing to consider is, well, if 7 of them can't grow, how many of them can? In that case, it's the difference between the 7 and the 10, because it shows at the start of the experiment there was 10. So, you know, if we look far, far into the past, we'll know there was always 7, right, initially, and those 7 can't grow. That's why there's a horizontal asymptote. So you have 3 that can grow, 7 that can't, and that's a really critical piece. So that represents our A value. That's how much we start with that can grow. So we have an A value of 3, we have a horizontal asymptote at 7, and that represents our D value. Right, that's a shift up by 7. Okay, that horizontal asymptote of 7. Okay, so let's put the numbers in and see what we can do. And we're going to pick an ordered pair again. And it doesn't matter which ordered pair we pick. Well, we should pick something. We don't want to pick an x value of 0 because we have to determine the value of b. So if I look at this, I'm going to pick an ordered pair, and I might do 4 and 55. So let's see here. I've got a y value of 55. The a value I know is 3, which is the difference between the asymptote and the y-intercept. And then it's b to the exponent of 4 in this case, because it's after 4 hours, plus d, and we know our d value is 7, because if I look far, far back in the past, I can see that there was a horizontal asymptote at 7. So my only unknown in this case is b. So in order to solve this equation, I have to subtract by 7, and then the other next inverse operation is to divide by 3. So subtracting 7 from 55 is 48. 48 divided by 3 is 16. So b to the 4th is 16. So we can either take the 4th root of both sides or exponent of 1/4. Both of those will work. Let's go over here and do that. And so what we have is 16 to the 1/4, and then b to the 4th to the 1/4. And so 4 times 1/4 is 1. So b to the 1 is 16 to the 1/4, and that's 2. So 2 equals b. So our repeated multiplier is 2, which we can actually see because we have 3 that grow initially, and then that goes, if you look at your differences, that's 6. And then if you look again, 31 minus 9 is 12, and I'm betting the next one is going to be 55 minus 31 is 24. So you can see right away the repeated pattern in multiplying is 2, because our differences are 24, 12, 6, and 3. So we would multiply repeatedly by 2 to generate that pattern. So the function then, the exponential function in this case, is going to be f of x equals 3 times 2 to the x plus 7, and in terms of our real-life context, that means we have 7 bacteria that cannot reproduce. It's a horizontal shift up by 7, and we have 3 bacterias that can reproduce, and you can see that in the y-intercept that there's 10 in total. So 3 that can reproduce and 7 that can't, and then the 2 refers to the base of the function, and that means it's multiplying by 2 or doubling every every time period, which for us is 1 hour. So that's how you generate exponential functions from data or from a graph.